I think it's time to start. So good morning, ladies and gentlemen. On behalf of the Béla Institute, I welcome you to the award ceremony of the Béla Szőkefalvi-Nagy Medal. In particular, I would like to welcome Professor Chi-Kwong Lee, recipient of the 2025 medal, Zoltán Szőkefalvi-Nagy, the representative of the Szőkefalvi-Nagy family, and Professor Zoltán Kónya, the Vice Rector of the University of Szeged for Scientific Affairs. So thank you for joining us today. The Béla Szőkefalvi-Nagy medal was founded in 1999 by Erzsébet Szőkefalvi-Nagy in memory of her father, Professor Béla Szőkefalvi-Nagy, who served as editor-in-chief of the journal Acta Scientiarum Mathematicarum from 1946 to 1981, so for about 35 years. This is the first year when Erzsébet Szőkefalvi-Nagy is no longer with us. We pay our respects to the memory of Erzsébet Szőkefalvi-Nagy, daughter of Béla Szőkefalvi-Nagy, who passed away in March 2025. Not only was she the founder and caretaker of the medal, she also made it possible that this tradition can continue and the medal can be awarded in the next decades. The Béla Institute and the University of Szeged are honored to accept this responsibility. The medal that you can see on the screen, the front side of this rose silver medal has the portrait of Béla Szőkefalvi-Nagy. Its backside contains the name of the awardee, surrounded by the inscription Acta Scientiarum Mathematicarum. The medal was designed and the engravings were made by the artist András Lapis. The medal is awarded annually by the Béla Institute to honor a distinguished mathematician who has published significant and deep results in the journal Acta. In 2025, the recipient of the medal is Professor Chi-Kwong Lee from the College of William and Mary in Virginia, United States of America, and University of Waterloo in Ontario, Canada. And now I ask Professor Lajos Molnár, the editor-in-chief of Acta, to present the mathematical works of Professor Lee. Please.
Thank you very much. So I would like to summarize or say a few words about Professor Lee's achievements, mathematical results. So I will present a short vita, which won't be very short, due to the fact that his achievements, his activities vary over a very wide range. So first of all, the areas of his work, I mean first the general areas, they include matrix theory, operator theory, quantum information science, mathematical education. And more specifically, he has done substantial work on numerical ranges, preserver problems, matrix and operator inequalities, quantum error correction. And as for the mathematical education, problem solving and including undergraduate students into research. His achievements in numbers, according to MathSciNet, the earliest index publication appeared in 1984, and up till now, the total number of his publications is 366, which is in mathematics, it's a very big number. As big as the number of his citations. So in MathSciNet, the number of citations is over 4,000. In Google Scholar, it's over 9,000. And he has very many collaborators, altogether 185, which I can count. And then, according to MathSciNet, one can create a table listing the different areas in which he worked and the number of the papers which appeared in that area. So you can see that the highest number of papers appeared in linear and multilinear algebra, matrix theory, and next operator theory, quantum theory, but we can find also combinatorics here, group theory, biology, numerical analysis, economics, convex and discrete geometry, real functions, and so on. So this is really a wide range of research work, what this table represents. Degrees and academic positions. So he received his PhD at the University of Hong Kong, and currently he has the following positions. He's Ferguson Professor at the College of William and Mary, affiliate faculty of the Applied Science Department at the same place, and affiliate member of the Institute for Quantum Computing, University of Waterloo. And yesterday I noticed on your, because he gave a talk, I noticed on the slides that now you are also in some connection. George Mason University.
Quantum Engineering Center.
Yeah, Quantum Engineering Center. Previous positions, so let's start with the beginning. So he was assistant professor at the University of Wisconsin-Madison, and after that visiting assistant professor at Johns Hopkins University, and then visiting positions. He had visiting positions at University of Toronto. He was honorary professor at several universities in China and Hong Kong, and was also chair of the Department of Mathematics at the College of William and Mary. He has been providing extensive service to the mathematical community. He had several editorial positions. Currently, he's a senior editor at the Linear Algebra and its Applications, and he's editor of Involve, which is a very particular journal. Namely, it's a unique academic publication dedicated to showcasing high-quality mathematical research that involves significant collaboration between faculty and students. He was editor-in-chief at Linear and Multilinear Algebra, and also founding editor and editor-in-chief at the Journal of Operators and Matrices. Other services at the International Linear Algebra Society, which is a huge, very big society in the area of linear algebra. He was vice president, served on the board of directors and various committees. Currently, he's the journal committee member. At the Applied Algebra and Optimization Research Center in South Korea, he was advisory board member for 6 years, and at the International Research Center for Tensor and Matrix Theory in China, Shanghai University, he was co-director. He has delivered countless colloquium and conference lectures and organized numerous international conferences and workshops, and he's very much dedicated to mentoring young students. He has supervised 4 PhD dissertations and approximately 70 undergraduate research projects. He received numerous honors, prizes and awards. Most recently, last year, he received the Hans Schneider Prize. Anyway, you are a kind of student of Hans Schneider, right?
Postdoc.
Yeah, postdoc, yeah. Which is the highest honor awarded by the International Linear Algebra Society. And now the results and papers. So his 15 most highly cited papers, each with citations between 50 and 200, according to MedSciNet. Those papers cover diverse topics, including numerical ranges, preservers, multivariable means, Hermitian and skew Hermitian splitting method, and Perron-Frobenius theory, and so on. The first paper I cannot avoid mentioning is his kind of survey paper or introductory paper to linear preserver problems with almost 200 citations. It appeared in American Monthly. And let me quote from the review. It says that the paper offers a gentle introduction to the theory of linear preservers. The authors describe the problem of the characterization of such maps, explain why those problems are attractive, present several active linear preserver problems not yet completely solved, and some techniques that have been successful in solving this kind of problems. Usually the question of what the general form of linear preserver is has an elegant answer. There are some interesting exceptional cases, and some of them are described. Anyone who wants to understand linear preserver problems will find a brief but quite complete explanation that is not too technical. The paper should also be read by anyone who wants to enter this research area, since it helps one to get a general overview of the topic. And this review was written by Peter Schemerel, who received our medal in 2018, currently editor-in-chief of Linear Algebra and its Applications, which is the leading journal in linear algebra, and also editor of our journal, Opta Szeged. The second paper I need to mention is the paper on the multivariable geometric means. It appeared in LAA, 170 citations, and there is a beautiful theory called Kubo-Ando theory of means. But those means are for pairs of positive semi-definite matrices or operators. And to extend from the two variable case to the multivariable case, this was a very difficult question, and many mathematicians worked on that. And as for the geometric mean, this paper was a very influential and very important paper. Here the authors present an approach to defining the multivariable geometric mean of positive semi-definite matrices or operators. The approach is axiomatic with the aim to define the multivariable mean such that it has a number of desired properties: homogeneity, monotonicity, congruence invariance, and joint concavity. The third paper I would like to mention is about the preconditioned Hermitian and skew-Hermitian splitting method, which is an iterative technique designed to solve large, sparse, non-Hermitian systems of linear equations. The author established a necessary and sufficient condition for the unconditional convergence of this method for non-Hermitian positive semi-definite systems, and as applications they extend the results to block three diagonal linear systems which appear in the numerical partial differential equations. And now let me just continue with mentioning the areas and some of the results without mentioning papers, okay? So he did a fundamental work on numerical ranges. According to MathSciNet, he has 210 papers related to this area. We know that the study of numerical ranges is a very important area in matrix theory and operator theory. The classical numerical range of a matrix is defined on that way, what you can see here. And there are several extensions, several generalizations. For example, the C numerical range, you fix a matrix, and then this is the definition of the C numerical range. And in the particular case, when C is this very simple diagonal matrix, this goes back to the original notion of the numerical range. And the other generalization is a higher rank numerical range, defined in this way, what you can see there. And to define this, the motivation came from the study of quantum error correction. Okay, I don't want to go into the details. When k is 1, so when here k is 1, so the rank here is 1, then again it goes back to the original numerical range. And the main contributions by him and his collaborators in this area, as for the C numerical ranges, the characterizations of the compactness of that kind of numerical range, elliptic shape, and rotational symmetricity. Concerning the higher rank numerical ranges, whenever we have some sort of numerical range, the question is the convexity. This is the number one question. And as for the higher rank numerical range, it was a very non-trivial question, so they proved that the higher rank numerical range is always convex, thus confirming a significant conjecture in the field. As for normal matrices, he demonstrated that for normal matrices, the range is this range is a convex polygon determined by the eigenvalues of the matrix, and he also established this dimensional requirement that would guarantee that the numerical range of the matrix A, I mean the rank A numerical range, is non-empty. Other related work, I did not speak about joint numerical ranges, but there is that concept, and he investigated the joint numerical range of multiple Hermitian matrices, focusing on their convexity, once again the convexity question, and algebraic connections to commutativity. Matrix polynomials, he made foundational works on the numerical range of matrix polynomials relating to their geometric properties, to stability theory and vibration systems. And as for operator theory, he did a lot of work and substantial work on dilation theory, and this connects him quite closely to Szeged, because Professor Szőkefalvi-Nagy was a kind of founder in this area, so he had fundamental results on dilation theory. What is the main question of this theory? Exploration, how a given operator can be represented as a part of a larger, simpler operator on a larger Hilbert space. Simpler operator means a unitary or normal operator. And his results on this area include the investigation of the numerical range inclusion. So he obtained important, actually they obtained important results relating the relationship between the inclusion of numerical ranges and the existence of certain dilations. Unitary dilations, he settled the conjecture by Halmos, showing that the closure of the numerical range of a contraction is the intersection of the numerical ranges of its unitary dilations. And as for commuting dilations, he demonstrated that for any n-tuple of operators, there is a common dilation to commuting and normal operators on a larger Hilbert space. Also, he had important results concerning operator inequalities and norms. Much of his research involves unitary invariant norms and inequalities relating to the spectrum, singular values, and norms of operators. He characterized inner isometries with respect to various operator norms. And now papers in Acta Szeged. Since 2020, he published 4 original research papers in our journal. They address several topics from his main research directions of numerical ranges, dilations, and unitary invariant norms. And here is the first paper on numerical range dilation, and the other one about joint K numerical ranges. And the third one, let me just speak a few words about it. So here he considers a certain class of unitary invariant norms in the following way. We have a symmetric norm on Rn, and we have a Hilbert space of arbitrary dimension. The only constraint is that the dimension should be at least n. And then one can define a norm on the space of all operators in this way. What you can see there. And here S1 and Sn, those are the singular values. In this abstract setting, the singular values are defined in this way. So approximation by finite operators with rank less than k. And he proved the basic properties of this norm, including some norm inequalities and characterization of the equality case, and established some geometric properties of the unit ball, and then using all those information, he determined the structure of the corresponding isometries, so maps preserving the distance between operators. And the fourth paper is about the C numerical range, and once again about unitary dilations. And there is a very recent paper, not long ago submitted. Maybe it is still in the review process. Yeah. This is about preservers on tuplets matrices. And anyway, yesterday in his lecture he mentioned several results from this paper. So, I'm convinced that anyone would consider Professor Lee's lifelong work, the accomplishments and contributions not only extraordinarily impressive, but more than enough to fill several human lifetimes. And undoubtedly, he is a driving force in the linear algebra community, and I'm confident that this will continue for many years to come. So, dear Professor Lee, congratulations. Congratulations, dear Chico. So.
Thank you very much. I thank Professor Warner for the presentation. And now I would like to present the medal to Professor Lee. It is a tradition that the recipient of the medal signs a marble plaque. So I ask Professor Lee that after receiving the medal, please kindly sign the marble plate.
Thank you very much. Congratulations. Thank you. Thank you.
Thank you. And now I ask Professor Lee to give his talk. So please come forward and.
Okay, good morning, everyone. It is truly my honor to be here to receive the medal. And I know that there are many very good and deserving candidates for the medal. And I am really, really flattered and feel honored to be chosen to receive the medal in 2025. And in particular, it was mentioned by Lajos that, for example, one of the colleagues, Peter, received the medal. And also on the list, actually, Professor Ando was another collaborator for the paper on geometric mean, was also one of the, actually, is the first Asian mathematician receiving the medal. And I even saw a pattern that in 2005, Professor Ando received the medal. 10 years later, another friend from Taiwan, Pei-Yun Wu, 2015, received the medal. So another 10 years, 2025, I'm so very honored to receive the medal. So I will continue to keep track on this track to see whether every 10 years would it be an Asian descendant recipient of the medal. And also thank you very much for all of you coming here, and thanks for Lajos for the very, very nice introduction. And so it saved a lot of time for my talk, so many concepts has been mentioned, and maybe we can end early. Okay, without further words, so let me start the journey. So exactly, I select a topic, which is my favorite topic, as mentioned by Lajos, is the numerical range and generalization. And it covers several decades, some related work of myself. And important thing is that for research area, we want to see the new meaning, new direction. So it will also include some new development, new open problem. Like the talk I gave yesterday, always I want to tell people, share what I know, but more importantly is what I do not know. Hopefully the audience will pick up the interest and then solve the problem, help solve the problem. So here we use the standard notation in operator theory. BH is the set of all bounded linear operator acting on a Hilbert space. And if dimension n, in my case, very often I focus on matrix. So finite dimensional case, we are really just talking about the Hilbert space Cn using the usual inner product and the Mn, n by n matrices. And then already seen in the previous presentation by Lajos that numerical range is just the collection of all the sesquilinear form, if you will, over complex, that the inner product between Tx and x, and with the norm-1 vector there. And then at Béla and Mary, myself also very interested in working with undergraduate student, graduate student colleague. Of course, I'm more than pleased to work with them. But working with undergraduate student, you always give a reason why you want to study some object, mathematical object. Could be very, very abstract, but to draw their attention, you give some layman way to understand what we are trying to do. So for the numerical range, I have an infinite dimensional operator, or a matrix n square, even. Nowadays, data science, you easily consider 1,000 by 1,000, 2,000, million by million matrix. You want to extract information from it. So numerical range is a easy way to capture some feature of the operator or the matrix. So I would tell students that, oh, it's just a picture of the matrix, which is very complicated in a high-dimensional space. So looking at the picture, what is the use? You look at the picture of me, maybe you can identify myself. If look at the picture, then the people first time meet me will recognize that it's me or something like that, or a tall man, short man, and something like that. So in the picture of the operator or matrices are useful in the following sense. It does not tell you everything. You cannot use a one-dimensional complex plane picture to tell you everything about the operator, but it does show some feature of the operator behind. For example, if the operator is a scalar operator, you can completely identify as seeing the picture being just a dot. So if the numerical range of the picture is very slim, just one dot, then no other choice. The operator must be a scalar operator. Also, if the picture you see, you collect all these points, complex number, they all happen to be real number, then you can conclude that the operator actually is self-adjoint. Actually, this is for other contexts in Banach space algebra, that is the way to define a Hermitian operator, so to speak, non-Hermitian operator. And for example, in quantum computing, we always deal with the so-called density matrices, how to detect that. So one rule is something with the numerical range of the picture, only a complex plane picture, only lie on the non-negative real line, it must be positive semi-definite. Okay, so, but you have to compute all the sesquilinear form on all the unit vector, right? Seems a lot of work. So now they're talking to students, they would say, data science, my instructor told me that you want to understand certain model, you only need to check a very small subset of the data set, then it is good. So I said, very good, exactly, the numerical range can do the same thing in the following sense. So if I give you random now, it is tricky to define random, right? So in quantum, they have the, so to speak, truly random selection of things. All other system is just pseudo-random. But just assume in a very loose sense of randomness, if you give me 10 vectors, 100 vectors on this huge system, this matrix, it always produces the same point. I would say even you give me 5, however you define random, you get a single point. I would bet $1 that is a scalar operator behind. It is very difficult to have a non-scalar operator when you hit this different quadratic form of unit vector, they always give you the same point. Likewise, if always give you the real number, then I would have high confidence that the thing behind is actually a self-adjoint operator. Okay, so even in the new meaning, telling students they are all crazy about this data science and then using small amount of information to give large amount of information, numerical range is still a very good tool. Okay, so exactly, I almost followed Lajos' presentation. The next thing I'm going to tell you is my interest in dilation. So what is dilation? Dilation is exactly when you can put a matrix, smaller matrix in a larger matrix. So if T is a Hilbert space operator, and if you can look at the operator matrix, you can fit it inside a larger one. The operator A is acting on a larger Hilbert space, therefore the operator matrix could be part of the, T could be part of the operator matrix of A. So that we call dilation. And then there's a dual concept which is called compression, that it is just the corner of a unitary similarity of that operator. And if you forget about the the garbage, it essentially says that you can get a partial isometry or reduce the dimension so that x star ax will give you t. So that is the dilation concept and compression concept. So, sorry, I always try to explain to students. Students immediately raise their hand saying that, hey, Professor CK or Chi Kwong, you're crazy. You just told us that we want to use a small amount of data to tell the feature of the large amount of data. A small matrix tells you the large matrix, or a collection of numbers tells you the feature of the large operators. But now you are doing the reverse. I have a small matrix, you want to find a larger matrix. Computationally, it's not efficient. It is unwise. But exactly already mentioned by Lajos, in this kind of study, yes, we sacrifice the number of data as a dimension, but we want to have a dilation with nice structure. It actually is very inspiring in data science. So nowadays everyone is talking about neural network, AI, how to generate large amount of data. You always think that you have a bunch of data, you select a small part of it, and hopefully that small amount of data can tell you the story, right? So if I use 10 parameters, I can tell Dow Jones tomorrow what happened, then I will be very successful. You do not look at hundreds and hundreds of factors affecting the stock market. But sometimes this tells us that it is not always unwise or foolish to put your set of data into an even larger set of data, which will reveal part of the feature is important. So that will be my advertisement to students, saying that dilation will not be such a stupid thing if you dilate it to a very nice structure that you can easily control. Then from that larger set of data, go back to the numerical range or whatever tool, you may be able to say something clever. So that is one philosophy why we want to do dilation. For example, in 60s, there's a result, and Harmon saying that every operator with norm less than or equal to 1, or you can normalize it so that the norm is less than or equal to 1, you can always put the operator matrix T into a double dimension operator matrix, which is unitary, and the construction is very simple. So now any unitary operator, the property unitary operator enjoy, you can see, how about this matrix, operator matrix, would it be nice? So you can do something about that. So that is an example of what I said earlier, okay? And go back to our first topic, is numerical range. It is it is very well known actually. The first few exercises about numerical range is that if you have a compression, or if you have dilation, depending on which one you are talking about, A and T, then the numerical range will be smaller. So basically, you are computing the quadratic form in a subspace. That is why you only get a part of the number of the larger guy, WA. Okay? So I said earlier, numerical range, hopefully, the picture of the operator can tell you something. So can we use this picture to tell us something about dilation? That is the question. So seeing that if T is a compression of A, then the numerical range inclusion hope, this picture will cover this other picture. Mathematicians always like to ask the converse. So if I have a operator and another operator, one picture covers the other picture, can I ensure that the smaller guy can be dilated to the larger guy as an operator? But this is absurd, because you can have a 1,000 by 1,000 matrix or even dimensional operator. The numerical range is very tiny. It will be inside a 2 by 2 matrix, for example, the numerical range of, well, you cannot dilate a 100 by 100 matrix to a 2 by 2 matrix. What do we do? Then the proper question is really, 2 by 2 matrix is very limited. But if I allow you to do tensor product, many copies of that. So 2 by 2 matrix is simple. The tensor product is not too complicated in terms of the analytic and algebraic property. And the thing is that this I tensor A, the numerical range will be the same as WA. So now the proper question is that, suppose I see that I can put this numerical range into this bigger picture, but the bigger picture comes from 2 by 2 matrix, what should I do? Oh, I can still try to make many copies by tensor product and see whether this I tensor A, many copies of A, will be able to generate T in the compression sense. So that would be the question to ask. And almost surprising that this is actually true in many nice cases. and related to different study eventually give this the answer of this question. So, of course, not every A will do the job. Exactly if A is 2 by 2, like I said, then it's okay. If you are willing to invest I tensor A, many copy of A, then whatever numerical range of T lie inside the 2 by 2 matrix numerical range, then I can do this compression or dilation. And the early result, as early as Ando, another 2005 medal awardee, and then Alpherson, in his from C-side algebra point of view, also obtained this result. And Choi and I later found out that, oh, it's not about, they do the case for the unit circle. So if the numerical range is in the unit circle corresponding to the numerical range, I mean including interior, represent the numerical range of a 2 by 2 matrix 0, 2, 0, 0. Then the dilation result hold. And then later we found out that, yeah, as long as it is 2 by 2 matrix, the numerical range will be an ellipse. So if you put the numerical range in the ellipse, then dilation happen using that WTA is a 2 by 2 matrix. And in other contexts, stay slightly differently, but eventually it's the same thing. If you can put your numerical range into a triangle, so Merman showed that, and Nakahara gave a very nice simple proof, inspire a later extension, that if you can put your numerical range into a triangle, then you can construct a 3 by 3 normal matrix with the eigenvalue using the 3 vertex. Then the dilation hold. You can use many of these 3 by 3 normal matrix to reconstruct your infinite dimensional operator. Okay? So 2 by 2 general matrix, 3 by 3 normal matrix is good. So in 2001, Choi and I unified these two results, saying that, oh, actually, if you have a 3 by 3 matrix with a reducing eigenvalue, but the picture of the numerical range will be just an ellipse and a point. The point go inside, you get the ellipse. If the ellipse degenerates to a straight line, then you get a triangle. So this extends the previous to the result. And I cannot help talking about this. The most recent work is indeed in the very nice journal I like. So we have a result there. Further extending this result, saying that if you have 4 by 4 with two reducing eigenvalue, but be very careful, the two eigenvalue isolated to form a straight line, and it can only touch the ellipse. Okay, so the numerical range will be the convex hull of that two eigenvalues shown in the picture, and the ellipse. Then you get a shape like this. Okay, then the dilation result also hold. Whatever stuff you can put inside this shape, you will have a dilation of that 4 by 4 matrix with these two reducing eigenvalue and that 2 by 2 matrix. Good? I like the saying of Bruce Lee. People know Bruce Lee, right? The Kung Fu martial art master. So at one point he told people in an interview, he said, "My friend, be water." Why? Because water in a bottle will be bottle, water in a cup will be a cup. So it reminds me that, oh, okay, look at dilation. Be water. You put it in the elliptical disc, then you have a 2 by 2 matrix dilation. You put it in a triangle, the triangle is your choice. You don't need to fix the triangle. Whatever triangle, you can enclose your numerical range. I can have a dilation of this form. If you do more complicated picture, like the third case and fourth case, same thing. So these are the cup and bottle inspired by Bruce Lee saying that for dilation, you can choose, you can select your shape, one of these four shapes. In any fashion, you like the triangle, you can rotate the triangle, choose any 3 point far away or 3 point just enough to include your numerical range, then you will have the dilation. Good? Yeah, I speak very fast. I hope it's okay, and I have some accent in my English. Still okay?
Yeah.
Okay, thank you. So, what next? Of course, we want the Bruce Lee's comment is true for any operator, which unfortunately is not true. There are limitations. So the 4 cases we show is already, up to this point, the best result we know about this dilation result. What kinds of shape you can put the numerical range in and guarantee a dilation of simple operator or simple matrix. So it turned out that even for general 3 by 3, remember 2 by 2 always work. 3 by 3, we require one existence of reducing eigenvalue. So essentially it's a single point direct sum with a 2 by 2 matrix. So in general, 3 by 3 won't work. So if you look at this case, the first matrix T0 root 2 0 0 will be circular disk, the numerical range, with radius 1 over root 2. And if you look at the Jordan plot, A1, 0 1 0 0 0 1 0 0 0, exactly the same disk you will generate. But there's no hope to dilate T into A1 because the norm condition ruined that. If it admits such a dilation, the norm cannot exceed the guy being the larger matrix, the I tensor A, right? But A1 has norm 1, T has norm root 2, so there's no chance to do that. The same thing, remember, Merman's result said that triangle is good. How about a four-side polygon? Square. So we look at the matrix with eigenvalue 1i minus 1 minus I, and the numerical range will simply be using 1i minus 1 to be the vertex, that square, tilde square. And then you can see that this choice just allows you to fit the circular disk inside this square, touching the four sides of the square. By the same argument I used earlier, T has norm root 2, but this guy T4 by 4, larger size doesn't count because the norm is 1, is a unitary. So impossible. Dilation is impossible. So at one point we talk about how about we impose, if norm is the obstacle, can we ensure that the norm of A bigger than T? Will it always work? And then in the 2001 paper with Choi, we show that no. So there's some intrinsic property about the operator you have to take care of. So for example, I take T and A equal, T equal to that weight shift finite dimensional matrix, and take the transpose. The numerical range actually are the same thing. It's a certain circular disk coincide. But even though the norm condition is not violated, it is not possible to do dilation using the operator structure. So even for this rather classical, and then my last paper is in 2020, still there a question. And actually, it's under active research. You can search. I know an Indian group, they are working on this problem, for example. So can you include the norm condition or what they call completely bounded map or contractive map? Would it be enough so to weaken just using the numerical range inclusion result, which of course is the simplest one to check, but you may need to add something. What to add is still a question. Okay, so think about the Bruce Lee situation. What kinds of cup and bottle you can form so that putting in, you will get a dilation. Okay, and Linus also helped me to link this work to, sometimes we are interested in unitary dilation. But then Harmus in 1964 indeed asked the question, is it possible to recover, right? So to recover in various sense. Earlier saying is that if the numerical range is inside A, and we use many copies of A in the dilation set, in the tensor product sense, I tensor A, to reconstruct the T. So you look at it in this way. So here's another way. Unitary is good. T admit a unitary dilation if T is a contraction. If not one U, can I use many U to recover that? So you express the numerical range of T in terms of the intersection of the numerical range of U, where U is the dilation of T. And then we do the closure result, because without closure, after Harmus posed that question 4 years later, just already showed that impossible, even for normal operator T. So without closure, things can be quite strange. But luckily, it could be done in the following way. So if you have a guy, the numerical range, this time what is my Bruce Lee's bottle or plate, I chop off the plate. So the numerical range inside the unit disk, that will be the result of Ando or Alpherson, or later Choi and myself. But if you do not give the full plate, you can only leave the numerical range in part of the plate, right? The other part reserved for, I don't know, French fryer or something, right? So if your numerical range is in part of the plate, shaded red in that picture, then can you do something? And the answer is that yes, you can do unitary dilation so that the unitary dilation, the unitary operator, also the numerical range lie on that part of the plate. But for unitary operator, the numerical range is decided by the eigenvalue. So it simply says that you can do the dilation, unitary dilation, by putting the spectrum on that circular arc on the left side. Left side, right? Yeah. So that is the result. And using that, we can use we can cut the plane in all directions to contain your numerical range, right? So your numerical range is this. Now I use another page, cut this, cut this, cut this. Each cut give you a unitary, which can do the inclusion. And then when you intersect those, then you will get the harmless conjecture with the closure condition. Rankine numerical range, also mentioned in Nayo's recent description of my work. So indeed, what is this? Quite funny, they consider the following. At one point, I don't even think that it is very attractive, but then this is actually the area. Let me go into quantum information science study. So my first paper on this area is exactly 2008, 2 years after this question was posed in the context of numerical range, and in particular related to dilation or compression. And I studied that. So it is another lecture to talk about quantum error correction and the relation with these kinds of so-called Rankine numerical range. But what I can tell you is the following. In a quantum system, finite dimensional, you always have error. Your data cannot be transmitted or kept intact because of time, because of the quantum decoherence, all kinds of quantum interaction with other systems. So if you put it in a matrix model, if you have an n-dimensional quantum state, if you understand the error operator, the effect on your system, then you can ask the question, what is the best I can do? I want to have, ideally, all the n-dimensional vector will be transmitted faithfully, accurately, from one system to another system, or in your quantum computing process, from one step to another step, every vector will be free from all this error attack. But there's another way. You understand the error pattern, and you try to find the maximum subspace so that your quantum state represented as vector will not be affected inside that subspace, or being affected, but you can recover. So that is the theory. And the matrix model turned out to be you consider a bunch of matrices. Let us start with one, so that you can find a corner, a compression, which is a scalar matrix, that exactly tell you the maximum dimension k. And if you have many error operator, you will have to choose a common corner. All of them are scalar. So that is roughly the motivation. So anyway, so people start from one operator. Very soon you will see the joint numerical range concerning several operators. So for one operator, how can you describe this set that you can use a compression to extract a scalar? What is the maximum size you can do? Like in the previous presentation, sometimes it could be empty. You can correct nothing if the error is too massive, right? So anyway, it gives rise to this study of Rankine numerical ranges, the compression containing a scalar matrix in general. Given n by n matrix, what is the k? Maximum k, or simply fix a k, how many the subspace containing some quantum error you can recover, right? So we do exactly the same trick, try to understand this set by using the intersection of normal. So extend the classical numerical range result answer of Harmos, which is a pure math problem, turned out to be very useful in this quantum computing context to analyze whether you can describe the set of Rankine numerical range, describe all the subspace you can do quantum error correction. And quite interesting, same thing, we can extend the idea of finding unitary, and even we can improve. In the previous result, if you remember, we say that if the numerical range is in part of the disk, then you can use double-size unitary. I didn't emphasize too much, but if finite dimensional is double size, if Hilbert space just pick another copy of the Hilbert space, then you can construct a unitary with the numerical range in the same restricted location, then you can do the job. So here, the result was extend, but you can even do better. Your dilation need not be double dimension, especially for finite dimensional. You can actually using the kernel of I minus t star t to tell how small you have to increase the size to do the dilation. Okay, so we have some result like that. So details is not so important. The idea can be extended, and it is useful even unexpectedly in some so-called applied subject, quantum computing. Okay? And of course, people are interested in infinite dimensional, that you can also do. So for infinite dimensional, double size, or unitary dilation can recover the whole thing. Remember, you do not use one unitary to completely describe the set. You use many unitary, a troop of that to do that. So that will allow you to do that. But quickly, we move to John numerical range. I already hinted, for quantum computing, you are not talking about one operator, that the channel is not governed by one operator, the error operator. You need many. So naturally, we talk about John Ranke numerical range. Before that, let me do John numerical range. You just pick A1 up to AK, and then you compute the John quadratic form using unit vector. So I like to do that kinds of thing. I tell students, yeah, one operator, you have one picture of a solo picture of one person. Now you have a group of operators you have to handle. They are related. So you want to take a group picture. So you take the quadratic form using the same pixel on that digital camera, you get the group picture. Can we get something interesting from the group picture, right? And for the group picture, quickly we identify that for some problem, may not be every problem, but many problems, look at the group picture, you can decompose each operator in their Hermitian decomposition, right? Aj as xj plus gj, where xj, gj are self-adjoint. Then the group picture will be what? You have k complex coordinate, which will be associated with 2n real coordinate if you separate them. So in terms of the picture, there's some result you may want to really use the complex structure, but purely looking at the geometry, you can look at self-adjoint operator by looking at the self-adjoint decomposition. So we often consider John numerical range of self-adjoint operator, right? But anyway, one very interesting result. Sorry, I'm getting old. I have to remember whether this has been mentioned. But anyway, that is one of the early results. Again, completely from pure study, that we see that, quite interesting. We can actually, the inspiration is from Merman's result. Okay, what's Merman's result? It says in triangle, any numerical range in the triangle, then you can do the dilation using the 3 vertex as the normal matrix. It turned out that Nakamura has a simple proof, Merman's result, and I said, actually, I remember pretty well, even though it has many years, it's done in 1991. But when I visited Paul Biding in Calgary, and then Doug Fanning was there, and then some dinner thing, and then we talk about this interesting topic. What the heck is going on? What is the proof? What is the simple proof? And we discovered that actually, Nakamura's proof can be extended to high dimension. Namely, if you look at K self-adjoint operator, the K numerical range will be in Rk, right? Self-adjoint, all those points will be real points. So again, we look at a triangle on R2, which simply is a simplex in R2. And the proof actually works for general K self-adjoint operator. If you have a John numerical range, which is in Rk, and if you can contain it in a simplex, which is a polyhedron with k plus 1 vertex, then that proof works. The dilation result works. The John dilation result works. So that is this result saying that if you have T1 up to Tk, the group picture, take the John numerical range, if you can fit that in a simplex, then it will work. So don't think too complicated. Think about Merman. The simplex is a triangle, 2-dimensional numerical range. 3-dimensional simplex is just a tetrahedron. So if you draw any tetrahedron, anything inside the tetrahedron, the numerical range, the John numerical range, which is still convex, by the way, 3 self-adjoint operator, the numerical range dimension at least 3, then it is a convex set. You can stuff it inside this tetrahedron. That guarantee you can have a John dilation. So that is the result about the John dilation. Okay, and then what? This proof turned out to be very simple if you do it right. So that is another thing. Sorry, I keep talking about my experience with undergraduate students and William Mary. So sometimes you show them a proof, finding a simple proof. So I mentioned that I always like solve problem, and finding simple proof is another thing. Some complicated result, if you can find a simple proof, it allows you to understand the problem better or even extend it. So in this case, wait until 2020. I think it's in the same paper in my favorite journal, that we say that, oh, okay, the result, this simplex thing, this geometrical thing can be easily handled if we can reduce it to the simple case. If your simplex, the Bruce Lee's region, in this case, the simplex is the standard simplex. What is the standard simplex in R3? You take the origin, 1, 0, 0, 0, 1, 0, 0, 0, 1, that tetrahedron will be the standard simplex in R3. R2, of course, is 0, 0, 1, 0, 0, 1. So you extend this to high dimension simplex. That case is easy to prove in the operator theory case. So if the simplex is the standard simplex and the joint numerical range is inside this guy, then you can, not too difficult to prove that you can do the dilation. But we need a tool. Very easy. General simplex n k plus 1 vertex in Rk, convex out of k plus 1 vertex in Rk, just apply an affine transform to bring it to the easy case. And we can show that the numerical range dilation and inclusion respect this affine transformation. Now I can disclose the secret. Why Alpherson and Endo have to do the unit circle and we can do the ellipse? It's just a affine transformation of the circle to ellipse. The dilation result will follow. Okay. So my trick is, I should not leave the range, but I want to get some water and slow myself down, so you don't need to hearing me keep saying non-stop. My student always come and I move too fast and speak too fast, so I'm afraid that this is my shortcoming. Anyway, so, and then actually, a new proof, as I said, to me, I benefit a lot from that, being not particularly careful mathematician. Sometimes you see a simple proof, then it allows you to move it to more general results. So it turned out that you can, not only the simplex thing, so the container containing the numerical range can be by affine transform and unitary similarity to some simple thing like, I suppose this one, right? So it's just basically a basic matrix unit and at most one symmetric matrix of 2 dimensions. If you can reduce your system, A1 up to AK, to something like that, even a subspace, in the span of this subspace, and you're in business. Again, too complicated to think about what it meant geometrically, especially R4 or above. Just think about R3. For example, we create another container for dilation. So it turned out that we can select 3 matrices in 3-dimensional, which form the ice cream cone, the numerical range. Then any ice cream you put in the ice cream cone, any joint numerical range of T1, T2, T3 inside the ice cream cone allow the dilation. So that is another nice picture I can show student using that particular result. Okay, so now go to a little bit operator theory and the second part of my title. How many times should I observe? Another 10 minutes or?
Maybe even more.
Oh, okay, so I don't need to rush. Yeah, I can speak very fast, and then, but no, I will not do that. So anyway, so we go to a more infinite dimensional setting. So I still use the self-adjoint for joint numerical range. So joint essential numerical range. What is essential numerical range? So you do operator A1 up to AK. You don't form the numerical range. That may or may not be closed. You take the closure. But what is essential? So most operator theory people, functional analysis people know that essential is modulo the compact operator, basically the behavior of the operator in the Coquin algebra. So you modulo out you walk out the compact operator, what would happen? Okay, so again, the story to undergraduate student is like, you're looking at the picture, the John picture of A1 up to AK. But there's some noise there, right? Exactly in data science. You want to remove the noise. So finite dimensional compact operator are the noise that could occur to your picture. So I want to remove all those. So you filter out all these compact operator inference. And what is the core thing? That is the essential picture the data contain. So if you can get to the guts of it, the bottom of it, then you get the most useful information in some study. But I went to the airport, right, traveling, and then they used the image recognition of my face, and then let me pass the security, let me pass enter the cabin. So, of course, there are many noise. That particular day, I have a band-aid there, maybe something happened to me, right? But if you can filter out all this and then still identify this is indeed the person, and go to through the security, that is good. So in general, for operator, we use all this filter to be compact operator. Again, I'm not a prime mathematician by training, but I can understand sometimes they want to do the same thing, a set of data. It's so messy, like garbage. But if you can remove the noise or whatever unnecessary thing affecting the core part of your data, that would be useful. So we want to do that. We want to do that. So in this study, of course, by definition, you can consider infinitely many all possible compact operator perturbation and look at the closure and look at the essential numerical range. But isn't it nice, and indeed very nice? I think Müller is also one of the recipients, right? Yeah, yes, last medal, right? So Professor Müller had this wonderful result. So the history was quite interesting. Poon and I have a result about this essential numerical range and star shapedness and so forth. And then I met Professor Müller the first time in a conference, and he approached me and said that, oh, your result seems to be useful. And then actually, I enjoy his talk very much. He's saying the following. The detail is not important, but in terms of the filter, is you use infinitely many filter to recover your essential numerical range, which is important in your study. You only need to use one filter, one compact perturbation. We cover that. It's almost too good to be true. The definition requires you to use infinitely many. I have yet to talk to a prime mathematician, right? You look at different filters to get good result. People even compete. This filter produce better picture in certain circumstances. What if I tell you that there's one filter can represent all the filter? So I don't know whether they have some study that allow them or require them or move them to construct one particular filter which will do the job of all other filters, give you the essential information, right? Philosophically, I think it's a sensible question, and then we want to do that. Whether we can do that, we don't know. But for essential numerical range, this is doable. Okay? But then we look at the John numerical range. So we go to another, sorry to put so many generalization to your head, but hopefully, step by step, you are okay with this yet another level of generalization. So we have the complex plane classical numerical range and the John numerical range on RK after we restrict to say a John operator. We have the rank K numerical range. So I briefly told you that it is related to quantum computing, quantum error correction. To find the quantum error subspace, you can do error correction scheme. But there's an earlier result is called the matricial range. You do not require X star AX to be scalar. When you do quantum error correction, you want that scalar, lambda IK, that corner. And you have garbage on the three other blocks, but that thing is a scalar matrix. But what if I just look at the K by K corner? So for a large set of data, I only have access to the left top corner, for example. So I have this infinite matrix as A1 up to AK, but I only look at the corner. Is it good enough to tell us something? Or I can adjust a compression, see different left top corner. Would it help? So this is this kind of numerical range. Even infinite dimensional operator K of them, I just look at the Q by Q corner. How much can I tell? If you require Q to be 1, then you are basically looking at the John numerical range. So if I allow you to look at 2 by 2, how much better you can determine the structure. In connection to the earlier discussion, we asked a question, and then I learned, I do not know. I only know that Professor Müller's result is very good. You can use one filter to filter the essential John numerical range of operator. But now, if this Q matrix, Q by Q matrix is K-tuple, can you also do the job? Can you also use one compact operator to do the compact perturbation and recover the essential Q matrix range, which require infinitely many compact perturbation? Some of you familiar with this would know that this is the size string dilation. Actually, we are talking about the image of a unit or completed positive map, but maybe not too complicated the definition. Just assume that you have the operator, you can look at the Q by Q compression, okay? And you can adjust by changing your X. And then you can define the essential numerical range, the range consisting of matrices. So you reduce the data, but still a lot of data. But anyway, we want to ask whether you can do one. And then after learning the result of Professor Muller, and also I worked with this early dilation to result, and I have the chance to go to IQC, Institute for Quantum Computing in Canada, to spend some time visit there, and then I met Van Porsen and Poon, Yudong Poon from Iowa State U also happened that semester on sabbatical. Three of us are there. So we talk about this. And then, of course, Van Porsen is very good at this completely bounded map and so forth. And then the essential numerical range, of course, he knows also very well. But we blend all these apparently different things together, and finally see that, oh, we were able to extend the result of Professor Muller to this complicated Q by Q matrix. Professor Muller's result is basically the Q is 1, so 1 by 1 corner. Now we can do Q by Q corner. Still, one filter take care of everything. You can use one filter, the compact perturbation, to recover the set obtained by the intersection of infinitely many compact perturbations. Moreover, which is not difficult, if you can do it for Q matricial range, then all the other would also be recovered by the same perturbation. You don't need to do it at every level. For the 1 by 1 thing, you get a perturbation, single perturbation like Professor Muller's result. 2 by 2, you may get another one. 3 by 3, you get another one. But no, if you can do it for the Q by Q case, then all lowercase you can use exactly the same perturbation. No need to find a new one. But what is the speed? What problem? It's the most aggressive thing you want. Not only I want for a fixed Q by Q, those matrix corner, I can use one perturbation. I want to find one perturbation once forever. No need to worry forever. So, still not, there's some puzzle result, open problem. The recent thing is with Doug Frederick and so forth. I'll tell you the puzzle result in open problem. So, K equal to 1. Smith wrote paper in when was that? 1980, already showed that if you have only one self-adjoint operator, remember I always consider a self-adjoint operator. If one guy is okay, you can find one compact perturbation, work for all corners, 1 by 1 corner, 2 by 2 corners, 3 by 3 corner. Anything inside that, you can use that one single compact perturbation to recover the Q by Q matricial range, the Q matricial range for all Q, once and for all. Here is the trick. It ends up that, for example, in the paper with Porsen, one thing is that we found out that it turned out that the dilation result for simplex has implication in this problem. So if the essential numerical range is a simplex, K plus 1 vertex polygon in RK for this joint essential matricial range, then again, one filter will work for all dimension Q by Q matrix. There's some intrinsic nice property about the simplex situation. And we do not check any Q by Q. Essential, I just check one thing. The basic essential joint numerical range is a K tuple, K real tuple, which form a simplex in RK. And if that is the case, trouble-free. All Q matricial range, I can use one single perturbation to take care of that. The paper in my favorite journal include the result. How about if you have two self-adjoint operator A1, A2, then you throw in identity, you get a three-dimensional linear space usually, if they are linearly independent. Then they call it this operator space. And if you look at these three matrices, you can generate a rank 1 matrix. Then it also, once and for all, only one perturbation for all Q matricial range, essential matricial range. Yeah. And turn out that the most important thing later, Paulson and myself and Poon observed is that it turned out why essential numerical range dictate everything is because if the essential numerical range can be brought to something A hat have that kind of dilation property I mentioned earlier. Anything inside will be a dilation. That is the connection. That will do the job. Right. So still, I cannot say I completely understand that, so I can put all these loose threads together that they are related, and that is why sometimes you can borrow technique and use technique to solve some of this problem. And the most recent paper, they are using C-star convex set. Again, I don't want to bother you with that. So, for example, we observe that for this problem, actually, if the John essential numerical range can be identified as the John numerical range of A tilde. So essential numerical range to identify this guy, and this guy end up to be the same as the numerical range of another A1 tilde, A2 tilde, AK tuple of operator, which are commuting self-adjoint matrices. Then it will also work. This is, you can find one guy. What does it mean it works? You can find one compact perturbation good for all Q matrix essential numerical range for all K. Right. And for K bigger than or equal to 3, general result is impossible in the sense that there are some choice of A1, A2, A3 that it won't work, or A1, A2, A3, A4, it won't work. So 3 or more, finding one guy to take care of all the situation is hopeless. For some A1, A2, A3 up to AK. But still, an interesting question is, which A1 up to AK allow you to do one size fit all theorem? But the most striking thing is that for two Hermitian matrix, which basically is A1 plus A2, one general operator, when it could be done or it could not be done, or is it true that every A1 plus A2 general operator, you can use one thing, one compact perturbation to take care of all Q matricial range is still open. And yeah, so it is related to some other conjecture that I mentioned in the paper of Fennick and myself and Singler. So if you're interested, so this is, at this point, it's still an open question. And there are some other related questions about how to even compute the matricial ranges tricky. For example, 3 by 3 Jordan block, one single operator. How to find all the Q, for example, 2 by 2 Q matricial range. So for that matrix, it is open, which is certainly related to this problem. You have to understand enough for general single operator A1 plus A2 to answer the question. Is it always true that you can do this, or you can find? If you can find A1 plus A2 which do not allow the single perturbation take care of everything, again, problem solved. So you know that it is not always true. Yeah, I think I've said enough, so I will close here. Hopefully, I can make more progress, or you can help me to make more progress. And I would welcome question and comment. Thank you very much for your attention. Cosmo.
Thank you very much for the talk. And are there any questions, comments, maybe solutions?
Yes, please.
I have two questions. First one is that if I remember well, then Berkowitz and Timothy has a result connected with this Farosh problem. Do you know this type of problem? So you have
Sorry, I have to stand
contraction, for example, and the question is whether the numerical range is the intersection of the numerical ranges of the unitary dilations. Right. Now, if I remember well, that Berkowitz and Timothy dealt with this problem.
Right. So usually,
what is the connection of their result and your result?
Right. It probably is some other kinds of, but maybe directly connected to this John numerical range of several operator. If you have two operators, the unitary group action is path connected. You always have connected set, and the topology is relatively well understood. But still, sometimes when you have more than two operators, you may have winding number generating something which is not connected That could be a problem. So Lajos mentioned that convexity, actually, you also consider star shapedness and simply connectedness would be a intermediate property you want to study. So what you mentioned, I believe, is related to the topological behavior of the kinds of generalized numerical range or joint numerical range. Would it create some kinds of non-simply connected set? So that could make the question even more difficult. So that is the part I'm aware of. Right. So any other particular feature you want?
So this was about the single operators, not towers.
Oh, okay. So the single case? No.
Yes, yes. You take a single operator, one operator only, and then the question is, if this was a Holmes question, whether the numerical range is the intersection of the numerical range of the unitary dimensions.
Right.
The single dimensions.
Right, right.
You mentioned this.
Yeah, so that is that result, right?
And I would like to mention that Durst was a member of this institute.
Right. In some situations, the singularity doesn't cause a problem, except that if the numerical range does not contain the origin, then you can say even more, they will be on a half space. So that will have some impact. The immediate thing coming to my head is that otherwise, those dilation result or the intersection of unitary dilation, the singularity does not affect those very much, but there will be other aspects I'm not aware of. But from those results, singularity is not such a big deal, right? But when you talk about compact operator and so forth, of course, whether zero is the accumulation point, that could make a difference now. Yeah, because I mainly focus on inside a finite dimensional operator, so that thing didn't come up. But maybe for even dimensional operator, you want to do the dilation or compact operator, the accumulation point, the zero in it or not, in the spectrum or not, would make a difference. Yeah, right. So sorry, no complete answer, but I can link something. I will follow up that and see what I can find out.
My second question is about the rigidity of numerical ranges. The problem is that you take a certain class of operators, and the question is that whether the numerical range of an operator in this class is determined by the numerical range, the shape of the numerical range. So if another operator has the same numerical range, whether they are, for example, unitarily equivalent. Go and Wu has nice results in finite dimension.
Right.
But there are open questions. If you consider other classes, for example, truncated sheets.
Yes.
So have you dealt with these problems? Or?
That is, so Gao and Wu's result, I understand they consider the S-class operator, which impose that the n by n has only the eigenvalue, none of them can be on the boundary of the numerical range. It should allow a one-dimensional higher unitary dilation. Then with that very restricted condition, then the shape of two guys, make it 2 by 2, that is actually a generalization of the 2 by 2. Two by 2 matrices are unitarily similar, if and only if they have the same numerical range, period. So sort of you extend this, if you have a n plus 1 by n plus 1, and then look at the n compression, then if the numerical range have the same shape, then almost they have to be unitary equivalent or similar, because too little room for the projection is n out of n plus 1 dimension, right? And then the dirty trick of my friend Professor Choi, Andy Choi, do is that, oh, if you allow me to have even separable dimension Hilbert space, any convex set, you can put the diagonal operator using those pawns as a spectrum. Then the numerical range take closure will be that set. So if you do not impose strict algebraic or analytic condition on the, like you said, the set of operators you are dealing with, that could be wild. So how to set up the constraint on the collection of operator and therefore they have close relation with the numerical range is indeed a very interesting question, but have to select carefully. And we hope we can liberate the selection. A larger class, they still can tell you a lot about that. That is what we hope, right? But since you mentioned Gao's result, I know that they something very nice thing about the S class, but outside that would be tricky.
Any further questions or comments?
Yeah, I forgot to tell that Chico was asked to apply for a special Fulbright fellowship, distinguished one, and
John
also
von
the
Neumann.
name of von Neumann is included there. So we applied, and yesterday or the day before yesterday, we received the answer, the decision about the application. So he got this fellowship, and he will spend several months. If everything, everything would be arranged from the administrative side. So there is high chance that he will spend several months in Szeged the next year and the year after. So we will have chance to work together. Not only I, but
Yep, another very high honor with the support of RIOS and also the department and the institute. So I submit this Fulbright Fellowship application. John von Neumann is for education and research instead. So I don't think I'm particularly very outstanding, but my things fit. So I research, I like education, and then submit a proposal with the help of RIOS and some other people. So I'm again lucky to be selected. So if things go well, I don't know, they said financially, or I don't know, the war will be over, or will be that an unpredictable situation. But if not, nothing strange happen, then the proposed activities will be from mid-February, 3 months, to mid-May 2027, I will visit here. And then the same thing happened in 2028. So it consists of 2 parts. And I will be extremely thrilled, and then will enjoy coming here to see you again, and then of course work with colleagues. Yeah.
that's the good news.
Thank you very much. Any more questions, comments? Well, if not, then thank you very much again.